The formation of a solution requires that the particles making up the solute and solvent disperse in one another. This can be illustrated by thinking about two different gases in separate containers isolated by a valve. With the valve closed, the gases occupy their own container and do not mix. Their motion is constrained by the valve. When the valve is open, the gas particles flow both ways through the open valve such that they occupy both containers. The gas particles originally confined to different containers have dispersed in each other and are now mixed. Because they are mixed on the atomic or molecular level, they have formed a solution. This will happen with any pair of gases in any proportion once the valve is opened. The dispersal of the gases and their mixing is referred to as spontaneous. When something is spontaneous, we mean that it takes place without intervention. You do not have to do anything else once the valve is open. The gases mix all by themselves. All gases will mix spontaneously in any proportion when unconstrained by physical barriers such as the valve. But why do gases mix spontaneously? Why don't they stay in their own container when the valve is open? You have to remember that the gas particles are in constant motion in random directions. With the valve open, there is nothing stopping gas particles from hitting the valve opening and traveling between containers. The motion of the particles is unconstrained. Furthermore, if the gases behave ideally, there are also no intermolecular forces between the gas particles to restrain their motion. Thus, gas particles will go anywhere and everywhere within the container, including through the hole in the valve. This is inevitable and leads to mixing. The tendency of gas particles to mix when unconstrained by physical barriers or intermolecular forces is related to a property called entropy. Entropy is a measure of how dispersed the particles are, how unorganized, or how randomly distributed they are. The less the particles are dispersed, the lower the entropy. The greater the dispersal of the particles, the higher the entropy. When there are no forces constraining the motion of atoms or molecules, mixing will always happen, driven by an increase in this quantity called entropy. When there are intermolecular forces constraining the motion of the particles, the situation is different and requires more thought. Let's consider mixing a solid solute with a liquid solvent to form a solution. The solid solute is represented as a set of ordered gray circles that do not fill or take the shape of the container. The liquid solvent is represented by a set of blue circles that are more randomly arranged so that they take the shape of the container but still do not fill it. Finally, the solution is represented as a collection of gray and blue circles randomly dispersed among each other, taking the shape of the container. Mixing the solid and liquid particles leads to each becoming more dispersed. The solution therefore has greater disorder than the solute and solvent before mixing. A better way to say this is that the solution has higher entropy than the solid and liquid before mixing, which in turn have a lower entropy. The increased entropy favors formation of the solution. In this case, however, there are intermolecular forces restraining the dispersal of solute and solvent particles. These intermolecular forces may be of any type, including ion-ion, dipole-dipole, dispersion, hydrogen bonding, or really any type of intermolecular interaction. The particles in the solid solute have intermolecular forces acting between them, and these interactions are generically called solute-solute interactions to indicate that they act between solute particles. The particles in the liquid solvent also have intermolecular forces acting between them, which are generically called solvent-solvent interactions to indicate that they act between solvent particles. These interactions restrain free motion of solute and solvent particles and therefore must be overcome to allow dispersal of the particles. This costs energy. If it costs too much, dispersal will not happen and the solution will not form. But it's not all bad news. When solute and solvent particles get close to each other, there are interactions between them that are generically called solute-solvent interactions. These interactions are attractive and help make it favorable for solute and solvent particles to disperse. When intermolecular forces exist between particles, the solute-solute interactions and the solvent-solvent interactions must be overcome for particles to disperse. This is encouraged by the increase in entropy that takes place when particles disperse and by the solute-solvent interactions that form when solute and solvent particles get close together. Let's look at this in more detail. Whether or not solute and solvent particles will disperse in each other is determined by a competition between the things working against dispersal and the things working for dispersal. The things working against dispersal are the intermolecular forces that create solute-solute interactions and solvent-solvent interactions. These interactions restrain particle motion and make dispersal unfavorable. The things working for dispersal include the intermolecular forces that create solute-solvent interactions. These interactions draw solute and solvent particles together and make dispersal favorable. In addition, dispersal is favored by the increase in entropy that results when particles disperse. The outcome of this competition is largely determined by how significant the solute-solvent interactions are versus the solute-solute and solvent-solvent interactions. If solute-solvent interactions are about as significant or more significant than the total of solute-solute interactions and solvent-solvent interactions together, then dispersal happens spontaneously and the solute and solvent are called soluble in each other or miscible. If, on the other hand, solute solute-solvent interactions are much less significant than the total of solute-solute and solvent-solvent interactions together, there will be no dispersal, and the solute and solvent are considered insoluble or not miscible. There is a precise quantitative way to describe this competition, and we'll talk about that later. For now, however, this description is powerful enough. It will allow us to qualitatively predict whether a solute and solvent will disperse in each other, which is the subject of another microlecture. Let's look at a specific example to put all this on firmer foundation. So what does the dispersal process look like for an ionic solid solute dissolving in water solvent? It looks something like this. The ionic solid is shown on the left as an alternating array of positive and negative ions. The solute-solute interactions are ion-ion intermolecular forces. Water molecules are shown around the ionic solid, and they are attracted to each other by a solvent-solvent interaction whose origin is hydrogen bonding. These strong attractions within the solid and within the liquid inhibit dispersal of the solid solute in the water solvent. Every once in a while, the more positive end of a water molecule will approach one of the negatively charged ions in the solid, and there will be an attraction between the solute and solvent. This solute-solvent interaction is an ion-dipole intermolecular force. An ion-dipole interaction is not normally stronger than an ion-ion interaction, but if the negatively charged ion leaves the solid and enters the solution, it can be surrounded by 6 water molecules. In the case of many ionic solids, this outweighs the restraint created by the solute-solute ion-ion interactions and the solvent-solvent hydrogen bonding interactions. A similar thing occurs for positively charged ions. The more negative end of a water molecule sometimes approaches a cation in the solid and forms a solute-solvent interaction based on ion-dipole intermolecular forces. If the ion separates from the solid, it can form 6 of these interactions, which compensates for the restraint created by the ion-ion forces. When this happens over and over again for all the ions in the solid solute, the particles in the ionic solid are said to be dispersed in the solvent particles. A solution has been formed because the things working for dispersal were more significant than the things working against dispersal. And that's the dispersal process.